This chapter is going to be over the electronic structure of atoms. So where electrons are located, the electron behavior, what an atom's orbitals look like, and how we can give the electron an address as to where they're at in an atom. Oh. So first we have to look at light, because electrons do behave like light, and so the very first scientists that started studying electrons were first studying light. And light is a form of electromagnetic radiation, and ER is just a form of energy that exhibits the wave-like behavior. So visible light is an example, infrared, ultraviolet, those are all examples of electromagnetic radiation. And all the forms of electromagnetic radiation put together form the electromagnetic spectrum, and that's what this next picture will be about. And all this ER will travel at the speed of light, which is represented by the letter C. So whenever you see a C in an equation, that stands for the speed of light, which is 3 times 10 to the 8th meters per second. So if we look at this spectrum, we have everything from wavelengths of soccer fields, like radio waves, have a wavelength from peak to peak as long as a soccer field, whereas all the way down to shorter, the wavelength can be shorter than a water molecule itself. And those are gamma rays. And those are very, very high energy waves and can be dangerous if not used correctly. And so if you look at this little part right here, that is the visible spectrum, what we can see. So from all the spectrums, all the wavelengths that are produced, and actually the sun produces all the wavelengths, the whole spectrum, but it is just that little tiny visible spot is the kind we can, very little, but they can be. And some of them are lost in space and don't get to our atmosphere and all that kind of stuff too. Yes. So properties of light. The wavelength is represented by the Greek letter lambda, which is that upside down Y-looking thing, lambda. And it's the distance between troughs, so from trough to trough or from peak to peak of a wave. The frequency that's another Greek letter, but we're going to just call it V since it looks like a V. But it's the number of waves in a specific time. So it's waves per second, which the units they give frequency is in hertz. So seconds is in the denominator, and that would be a hertz then. So wavelength and frequency are inversely related to each other. We can use this equation where C is the speed of light, 3 times 10 to the 8th meters per second, is equal to lambda times V. So here's lambda, 2 pictures of lambda. Which one has a higher frequency? The bottom one. It has a higher frequency but a lower wavelength, a shorter wavelength. So you can see they're inverse of each other. And up here we have a higher wavelength but a lower frequency, so they're inverse. So if we have this problem that we're given the speed of light as 3 times 10 to the 8th meters per second, and we want to calculate the wavelength when the frequency is 7.5 times 10 to the 12th, we'll use our equation C equals lambda times V. So C is 3 times 10 to the 8th. Let's change that to yellow. And we're looking for wavelength. It's equal to, not equal to, times 7.5 times 10 to the 12th. One thing to note, since the speed of light is in meters per second, what units will lambda need to be in? Meters. It's a length, meters. So they give us lambda, or give us wavelength, make sure it's in meters before you plug it into this equation. Wavelengths, a lot of times, since they're really tiny, most of the time they're really tiny, then you're going to use nanometers. So you'll see nanometers a lot. How many nanometers are there in a meter? Do you remember? A million. Well, I only know this. 1 times 10 to the 9th. Is that a million? No. 10 to the 9th. Billion? Billion. 10 to the 9th would be billion. Yeah. Nano means 9, so 1 times 10 to the 9th. That's how you can do that. Yep. So what do you... Hertz is per second. So like... Nope. So what do you get for lambda here? 4 times 10 to the negative 5th. And this would be in meters. Good. Simple equation, just making sure you have the right units there. Negative 5th, yep. So the photoelectric effect is when certain metals when you shine light on certain metals, it'll emit electrons. And the amount of electrons emitted will depend on the frequency of light. And so Max Planck was actually studying this. And we'll look at his apparatus here in a little bit. But he saw that the metals emit energy in small specific amounts called quanta, and you can only release like 1, 2, 3 quanta. You can't release 1.5 or 2 2/3 quanta. And that quantum, there's certain frequencies that will make the metal emit those electrons, and those are called quantum. And it all relates back to frequency. So he made this equation that related energy and frequency together. Can I switch it? No. How about now? Yes? Oops. Here's that picture. Let's look at that first. So here the light is striking this metal, and there's an anode here that's kind of collecting or seeing how much electron is being produced, because it's hooked up to some voltage source, so it can measure how many electrons are being produced. And so that's how they studied this. But the equation he came up with is E, which is energy. Energy is in joules, a big J. Energy is equal to H. H is Planck's constant, and that is 6.626 times 10 to the negative 34th joule seconds, always. And then V, which is frequency, we've looked at that. So as the frequency of a wave goes up, the energy of the wave goes up. The frequency goes down, energy goes down. Negative 34, yes. Joule seconds. Joule time second. I don't know how, I can't remember. I watched a video on how he found it. It occurs a lot. It is in a lot of different equations, actually. That frequency. It doesn't have to do with charge, because it has to do with joules and time. But it's not per time. Could could happen. It's happened in the past. So Albert Einstein was studying the same phenomenon, and he was looking at just light itself. And so he came up with this idea of the dual wave particle nature. And he called these little packets of energy photons. So it's a little photon is a little packet of energy that's riding on this light wave. And it carries along a little bit of energy, a little packet of energy. So he just kind of tweaked that equation and just made it for the energy of a photon. So I have this little thing to show you the dual wave particle nature. So the light has these little packets of energy, and they can actually do work. And so if I shine this at here, it will actually make something move. So it's doing work. That's just an example of the dual wave particle nature. It gets to a certain point where it won't. And this light, it will usually go faster, but my battery's dying. Yeah. Direct sunlight will make it go really fast, actually. Okay, so if we do these problems, where we're looking at frequency, and we have an energy of the photon is 1 times 10 to the negative 24th. So our energy is 1.55 times 10 to the negative 24th joules. That's equal to Planck's constant, which is 6.626 times 10 to the negative 34th times V. So I'm looking for V. What would V be? Yep, E equals HV. So you're going to have to remember how you do the exponents on your calculator. Make sure you have exponents all right. Yes. What do you get? In scientific notation. Make sure you put parentheses around your numbers. And that is in hertz. Okay, this next problem is very similar to what we'll do in the flame test lab tomorrow, where we're going to have different metals that we're going to burn and look at the light that they produce. And certain colors of light correspond to certain wavelengths of light, and we'll be able to figure out what the frequency and energy of that light would be then. So here, sodium is heated in a yellow spectral line, has energy is 3.37 times 10 to the negative 19th joules per photon. They want to know what the frequency is. So if our energy is 3.37 times 10 to the negative 19th, that's equal to Planck's constant. That's a 3 times V. Probably get another big number. You guys agree? Yeah? So now, if they want to know the wavelength of this light, what would we do? Is there a way we can relate frequency and wavelength to each other? C, which is 3 times 10 to the 8th, equals lambda, which is the wavelength, which is what we're looking for, times 5.09 times 10 to the 14th. So what do we get for lambda? Meters. -7th. 5.89 times 10 to the -7th meters. Meters, correct. Questions on that? So now we could go backwards through that process where you're given the wavelength and you need to figure out what the energy of that wave is. So you go wavelength to frequency and then plug that in to the other equation and get your energy. So you can use those two equations together. Okay, and then this one, I think we're going to just do the top one. You'll do these two exactly the same. So we're just going to do one of them. We'll do the top one. Because this time, we're going to calculate if the energy in wavelengths, or the energy in joules of a photon with a wavelength of 5 times 10 to the 4th nanometers. What do we have to do first? Change it to meters. Because we're going to use our C equals lambda times V. And C is in meters per second, so we need to change this to meters. So I said 1 meter is equal to, this is nanometers, 1 times 10 to the 9th nanometers. So what? Right, we're moving the decimal 9 times to the right or left? To the left. So now we can carry that into our equation. 3 times 10 to the 8th is equal to, this is lambda, 5 times 10 to the -5th, and find frequency. And if we're looking for energy, now we can plug that into E equals 6.626 times 10 to the -34th times this frequency. So E is equal to what? It's per second. Like, we're talking about waves, so it's waves per second, or you could have like cars per second or rotations per second. Like if you're counting how many cars were going by or something. No. No. What do you get for energy? Anyone? 8.97? 3.97. Times 10 to the what? joules. 3.97 times 10 to the negative 21 joules. Good. It'll be okay. Okay, so we kind of talked about this slide already, where only whole numbers of photons are absorbed. You only absorb 1, 2, 3 photons. For electrons to be emitted, it has to be struck by a photon with a minimum energy requirement for that metal. So each metal that they were looking at had a different energy requirement. And the energy, again, corresponds to frequency. So what they started seeing is that when different elements were heated, especially gases, we're going to look at some gases here. When gases are heated, when they have energy given to them, what actually happens are these electrons move up to energy levels into excited state, and then they drop back down to ground state. They're going to emit light back out, and we can measure that light then. So ground state is the lowest energy state of an atom. And if we think about it like potential energy, where the nucleus, the farther away from the nucleus you are, the more energy you would have. Ground state would be the closest that an electron can be to the nucleus then. Or excited state, where you have higher potential energy, you're going to be farther from the nucleus. And the atom will give off energy when returning to ground state. So electrons, or the atoms in general, will go up to an excited state, and then when they drop back down to ground state, they're going to release energy. They have to gain energy to be moved into excited state. They'll release energy in the form of light to go back to ground state, which is how fluorescent lights work, or neon lights. That's how they all work. So what we can see are these line emission spectrums. Whoa. When you look at that light and you pass it through a prism, you see these certain bands of light. So hydrogen will emit a pink light. When you pass a current through it, you use electricity a lot to give it the energy that it needs. When you look at it with the spectroscope, there's a specific line spectrum. So you'll see these dark bands of color, not a continuous color. Like if you have a prism in the window and sunlight hits it, you see a rainbow on the wall. It'd be, if you had hydrogen light, just hydrogen light hit it, you'd see just dark bands of color instead of a continuous spectrum. And so this began Bohr came up with the model, and then we have the quantum theory that will help explain this also. These are spectroscopes, so we'll actually look at a line spectrum. So I should probably explain how to use this. Look through the skinny, narrow end. There's a hole there. You point that at the light. There's a little tiny slit off to the side. That's what you need to point at the light, and then look off to the side, and you'll all be able to see the dark bands of color. That's a line spectrum. So go ahead and use those. Pass it around. You have to actually point it at one of the fluorescent lights. Now, fluorescent lights are a mixture of gases, so we'll see. You guys all see it when you're looking through it? Okay, once everyone's seen through the spectroscope, I want you to compare what you see with the fluorescent lights with the sunlight. So I'm going to go back to the window and look at it also. Okay, go back to the window. Once you've looked at the fluorescent light, take the spectroscope back to the window and see if you can tell a difference between the lighting. Are you okay? Infrared, yep. What are you guys seeing that's different? It should be, the sunlight should be a continuous band of color, right? You don't see the dark bands like you see with the fluorescent light. Blurry looking. It all blends together. Yeah, it's a continuous spectrum. No, that's college chemistry. They haven't done that, actually. They haven't. So the reason why we see that different coloring is because the sun will emit all of the visible light wavelengths, so it should be a continuous spectrum, whereas the fluorescent lights, gases only produce certain wavelengths, and so you'll see the certain colors of light. Which is why, I don't know if you've noticed, if you go to the mall and buy something and you take it out in the sunlight and it looks a different color. Has anyone ever noticed that? No. It's because color is just a reflection of wavelengths, right? A reflection of light. So sunlight, since it produces all of the spectrum, it will reflect all the wavelengths possible, whereas fluorescent lights only produce certain wavelengths, so it only reflects certain wavelengths, which then changes the color a little bit. Okay. So here, this is just a picture of what you guys saw. Let's see here. So Bohr tried to explain these line spectrums, and he said that electrons were rotating on this orbit like planets around the sun, and that they don't move away from that orbit. When they get excited, they move to excited state. They're moving from one orbit to another, but they can't be in between orbits. His model was good for explaining hydrogen. Once you get past one electron in an atom, it wasn't so good. So that's why we're going to move on into the quantum theory, which is how they explain the rest of the gases. So this is called, Bohr's model is dealing with orbits. They're two-dimensional. And the quantum theory, we're going to go to a three-dimensional orbital. Can I switch it? No. This really might be it. How about now? No. I think this is, I don't know. Oh, that's just a picture of Bohr's model. So here's an example where on the left, the electron had to gain energy to move up to excited state, and then when the energy is released, when the electron moves down, and you can see there's different orbits that it can move up to. So it could go from this E1 all the way up to E3. That would take a certain amount of energy, different from going from E1 to E2. And same when they release energy, there's different wavelengths that would be released then, based on the energy levels they're dropping. it absorbs it.